Okay, so we are happy to have a last speaker of this morning's section, and he's Kai-Wang Ng from Academia Sinica, and he's going to tell us about primordial black holes or modulations in axion monodromy equation.
Yes, I'm sorry in the beginning because some of you may have heard this already, and I promise I still have some new stuff on it. Yeah. And it's kind of running late. Everyone is hungry, including myself. So, and I was told that our talk will be put on YouTube. And as a government employee, I could not do it lousy because it's public. So I don't know what to do. So just fill up. Okay, this is the title, and the only thing I think I connect to the string workshop is the axion monodromy. Monodromy, I just know the word, I don't know the content. You guys are expert, I'm a layman. So tell me more after my talk. Yeah, I just make use of the potential that you guys give me to do some interesting cosmology. And as everybody knows, this guy realized large field inflation. The whole Stanford group, because the Silverstein and Linde is there, so they need to do something great there. So they realized that Linde is a chaotic inflation, and we will look at that potential later on. And some interesting from this axion monodromy inflation, for example, I'm not going to talk about this, but I will touch on that. And this is not the main goal of this talk. The main goal is the primordial black hole. And they do have some speculations, as I will talk about these observations in matter power spectrum, as we can see in CMB and isotropies. But there's a caution: it's still consistent with a flat standard CDM. We don't see any significant oscillations in the CMB power spectrum, but it's fun to do that. And notice that the axion must couple to some standard model particles, and some people propose this trap inflation using the interaction between the axion. And the axion is the inverton, and to standard model particles or some particle at high energy scale, and they will give a successful inflation, even though with a steep potential. You've heard a lot of things about the flat, successful inflation need a flat potential, but in this model, we call this trap inflation. Even a steep potential will give you a very successful inflation. And so there's one thing in our mind is that in this trap inflation, we might produce primordial wave easily. This is the goal of this talk today. And because we really don't have time, and this is a field graph, I believe you have seen it before, and this is the inflation period, and this is the hot Big Bang. And during inflation, one main job is to produce fluctuations to seed the gas formation later on, when the fluctuation ends, we end the hot Big Bang. Just enough. Okay, and I don't want to skip that. And also, you have seen this very nice the temperature fluctuation on the sky, on the CMB sky, and what's called oscillations. And this one, the lower panel shows you the deviation from the mean. And this is the red line is the expectation for lambda CDM model. And this is the data. And this is you can see the fluctuation from the lambda CDM model. And this is so-called the oscillation. And it's just warn you, it's only it's not significantly, it's not statistically significant, but it's fun to play around it. Yeah, this oscillation. And sorry. Okay, and this is come to axion monodromy inflation, and the upper part of this this field I don't understand, and you can tell me later on. And just use this potential for the inflation, and this is the induced normal terms from this wrapping, the non-trivial winding number, and it gives you a large field inflation. Linear P is given by this value. Okay, let's just look at P equal to 2. This is the well-known Linde's inflation. This quadratic in phi. We call this Linde's chaotic inflation. And also, there are some modifications, cosine term, cosine potential due to, they call this modulations. It may be due to instantaneous effect or some other effect in the short dimensions. And today we just look at this potential and how do we use this potential to call up some interesting phenomenon for the experimentalists or observations to look at. And first of all, just tell you some history about the modulations. There's an oscillations in matter power spectrum. Because it's cosine term, it's periodic, it may have chance to produce these oscillations. Because this cosine term, they modify this is modification to the linear flat potential. So there may chances to produce oscillations on the power spectrum. And then the power spectrum imprint on the CMB and so on. People have worked very hard on that already. And today I'm not going to talk about these observations in CMB because the main topic is the primordial black holes. And the primordial black holes is very old topics. But people argue that the primordial may form at high density contrast, and also they can produce over a wide range of masses in the radiation dominant universe. But of course, we need, where do we find this high density contrast? This is the problem, the main problem to form primordial black holes in the early universe. And on the other hand, there has been very stringent limit on the primordial black hole masses. And actually, before LIGO, the window has been closed already. We cannot form primordial black hole. They can destroy the CMB and isotropy, emit to gamma waves. It's closed already. But after LIGO, people like theorists, especially, yeah, some constraint is not really it's kind of loose, and they open up, of course, the target LIGO black hole. They open up this one, all between primordial between 10 and 100. It's not quite yet closed. So if this window is allowed, and so we have chance and to produce primordial black hole within this mass range, and it could be the black hole observed by LIGO. And there's a papers that argue about that. And they say this window is still open, and actually the LIGO black hole actually is a primordial black hole. And one very important side point is this primordial black hole, they form during radiation dominant era, and they are very massive. That means they move very slowly. They really like the cold dark matter. And so another important is primordial black hole is baryonic, but they really they move very slowly. And
so I have a very last question.
Okay, no.
Okay. So how is primordial black hole different from? Well, okay. So let's say you cannot really tell the can we tell the difference between primordial black hole and the usual kind of normal black hole, like they form from the death of the stars.
Yeah. This is
And
the conclusion.
can we actually tell the difference from, say, some other well, okay, you can't see electromagnetic radiation from a black hole, but can you say like merging with other object like neutron star or something? They have a different electromagnetic.
Yes,
radiation.
yeah. I will talk about it in the conclusion.
Oh,
Just
okay.
a very short conclusion.
Okay.
But okay, just.
But what's the difference?
Yeah.
What's the difference usually from the astrophysical black hole?
Yeah, this is very important issue. Yeah.
Okay, so okay, you're gonna tell us?
Yes. Not tell the answer. Yeah, just tell on that. And people now worry about the synthesis. Yeah, if the dark matter there's too much baryon during the synthesis. But luckily they are black holes. They don't participate in the nuclear reaction during the synthesis, so they're not harmful. This is a very interesting point. And so what's the textbook information about the primordial black hole? And they could form in, for example, the quark hadron phase transition in the universe. But those black holes are small. It's around or less than about the solar mass. And so it seems that in the radiation-dominated universe, it's very difficult to produce black hole bigger than a stellar mass. And LIGO observed 10 or 30 solar mass. So the only thing we can think about is inflation. Yeah. And this is what I want to say about today. And again, during inflation, we generate some fluctuation and hope they collapse. When this fluctuation, we enter the horizon. But we have learned from WMAP, we have just learned from WMAP. Sorry, I can't. The fluctuations generated during inflation is a small number, 10 to the minus 5. That's we have seen it. Or the CMB sky, delta T is around this number. So the fluctuation could not be too big enough to form black hole when the fluctuation we enter the horizon. And yes, the clever people, they call up some funny infinite potential such that the power spectrum is very blue, and they could produce a lot of primordial black hole at the end of inflation. But if we form an end equation, sorry, the black hole is still too small. You cannot account for this LIGO black holes. And so there's many good ideas, hyperinflation, double inflation, in order to boost those small scale up to a bigger scale when we enter the horizon, to give you a bigger mass primordial black hole. And this is the background about the primordial black hole inflation. And today I'm talking about trap inflation. Trap inflation needs interaction. And for example, this is the inverton potential. I have some very light scalar field. Scalar field is coupled to inverton, and this is one of the examples for interacting inverton. Another for this talk, I will talk about this axion. We talk about the axion inflation, and so for axion, this is the axion potential for driving the inflation. And you talk about axion. Axion like to couple to photon, for example, FF tutor. This one just like the E dot B term. And what's the use for what's the interaction about? What's the trap inflation about? The trap inflation is this is the inverton potential to drive inflation, and the inverton is coupled to photon. When it rolls down the potential, and the inverton will convert into photon, and there's a very big back reaction from the photon production on the motion of the inverton. So even though you have very steep slope, because when it's rolling down, it keeps producing photon, and we will just push the photon back. So just effectively, the motion is slow rolling. And this idea of the trapped inflation. And I just give you an idea. This is the background reaction. We have seen this many times. This is the mean field of the photon rolling down the potential. And this is the back reaction due to the photon production. And now we want to calculate the fluctuation during inflation, the fluctuation on the axion field. And without the photon production and the beta equal to 1, and this term vanish, and this is just the quantum the Hawking fluctuation. Now we have back reaction because of the photon production. We have this back reaction term as a fluctuation term. It's pushing the axion all the time, and it will give additional fluctuation on the axion. And sometimes you will expect some dissipation term due to the particle production. And I just give you an example how this photon production work. And first of all, we look at this quadratic potential to drive inflation. And without photon production, and it will follow the red dashed line, and this slow rolling, and then it speed up, and it rolls towards the ground state, and the scalar field oscillate, and this is the standard quadratic inflation driven by this potential. But with photon production, we have this term, and due to the photon production, and you can see inflation, it will slow down the scalar field and prolong the e-folding, prolong the duration of the inflation, and this is what we observe. So this is the standard quadratic inflation without photon, and with photon production, it will prolong the inflation because it's just keep pushing the photon and slow down the inflation. You have a longer duration of the inflation, and this is a very explicit example of this trapping kind of inflation. And this blue line gives you you can think about this the degree of production of photon during the inflation. And you can see at this period, during the last 10 evo, there's a lot of photon production. That's why it will slow down the inflation, and you should have more e-foldings. Okay, now the main thing is to calculate the density fluctuation due to the photon fluctuation. And this is the result for different coupling constant. Sorry, I forgot to really tell you the coupling constant alpha here. The coupling between axion and photon, I call it alpha, and different alpha. The alpha 33 and smaller, alpha smaller. And you can see the photon production could really boost up the photon fluctuation or the density translate into the matter power spectrum. And you can see near the end of inflation, and we have seen at the end of inflation there's a lot of photon production, and it will kick the curvature fluctuations to a higher value. And I don't have time to talk about this one. Is the black dot line is so-called the primordial black hole bound, and it's translated from what? From astrophysical and cosmological constraints on the primordial ring bound spectrum. So if so far we haven't seen any primordial black hole, or from astrophysical or cosmos arguments, we can set a bound. We can set on the bound how much primordial black hole in the universe by mass, and this is we call this primordial mass fraction bound. So you can see in this trap inflation example, you can see you can rule out, if you believe this bound, you can rule out all this model because it produces too many primordial black hole. So you can just rule out or put a constraint on the coupling alpha. And now come back to this axion inflation with modulations. We have seen this. This is the quadratic inflation term, and this is the modification due to this wrapping. And this the red dash line is the quadratic term, and this is the modulation. The blue line is the potential, really drive the inflation. And what we got in this one, and the red line is the trajectory of the infinitron. You can see just it starts from 10, very far away from the bottom, and it move, and this is the you can see the time of the inflation, and it moves down and then stay, because you can see we have this blue line is tell you the degree of production of photon, and because at this period we produce a lot of photon, then the infiniton slow down and stuck at this value for a while, and then to end the inflation. And at the end is also where a lot of photon production at the end. And the main thing is to calculate the curvature perturbation due to the photon, due to this idea. And you can see, and at the beginning of the inflation, we have to keep the this to 10 to the minus 9 because of Planck or WMAP data. The fluctuation on very large scale have to be very small. That's what we observed. So we have to keep the delta, the density fluctuation small during the 10, 15 e-foldings after the start of inflation, and because of this photon production, and it push up the delta to some value, and then it go down like this. And this one actually is the model parameter we use in the modulations.
Sorry, what's the typical energy scale of those photons?
Energy scale?
Yeah, what kind of, how many, what in a time cube, what do you need?
It should be of order of the, at each time it should be order of the axion mass, because it's just, you can.
So therefore it's about the inflation scale.
Yeah, inflation scale.
So why is the in your model, what kind of scale it is?
Oh, see, for the axion mass it's around 10 to the 13 GeV. Yeah, it's a very high energy scale.
So why aren't we seeing those in the astrophysical? Can we actually see this in some kind of like cosmic ray?
First of all, you need to produce those axions at such high scale.
No, but you have photon. You have photon.
We have photon.
Yeah,
Oh, you mean?
Yeah. Why can we observe those photons in a high energy?
Oh no, this is really during inflation. Yeah, it heat up the universe. It heat up the universe at very high temperature. Yeah. And you can remember this photon is really the radiation, and we heat the universe at almost gas scale. Yeah. So it's a hot. Yeah. And the main one is we can, in this kind of model, the modulation can produce very big fluctuations during inflation, and this big fluctuation, when they re-enter the horizon, they can form primordial black holes in this mass range. And this is the main thing I want to. And actually, this you can say this really model dependent. You have rehabilitated It's really model independent. And even though I can change the modulations, and we can produce different primordial black hole with different mass range. This I really complete embedded. It's really model dependent. Yeah, and you can see one panel is missing because my student is still working on this supermassive black hole. Okay, just the end. Good. Yeah, we can go for lunch. Yeah, and binary black holes observed by LIGO may be primordial, and it's interesting. This primordial black hole could be a dark matter. And of course, it's a very sad news to particle physics community. And so no neutrino, no axion, no Higgs particle, dark matter, and it's all primordial black hole. So it's a very sad news if it's really true. And we have seen how axion, the axion, we try to use the axion homodromy inflation potential to produce primordial black holes. And we have seen some examples. Yeah, the modulation can really produce this LIGO black hole. And in fact, it's very model dependent. We can produce a very wide range of primordial black hole mass as well. And back to the question, how to distinguish primordial black hole from SO black hole is very important issue. Yeah, it's all, so far it's all speculations. Yeah, how to realize it. And there's some papers. For example, the primordial black holes, yeah, the spin, yeah, should be smaller than the astrophysical black hole, or the other way around. Yes, something like that. Yeah, using the spin, yeah, for example, the LIGO can measure the speed of the final product. And for primordial, the spin of the final merged black hole should be smaller than astrophysical one. That's one of the handles to distinguish two pictures.
So what do you mean by small?
The primordial.
You just learned that before, like we thought that primordial black holes can be only solar mass scales, and now we're using all kinds of models which can produce primordial black holes or supermassive primordial black holes, etc. So can't it be model dependent that the spin also you can
produce? The spin is kind of statistics in, for example, this is quantum fluctuation. I can imagine this all you have average. It's all statistics, yeah. And on average, the spin should be small. It's an intuition only. It's the origin is different. For astrophysics, they have equation this and this whole history. But for inflation, there's quantum fluctuations. This is one of the difference. And of course, another important thing is the CMB non-Gaussianity. Even though the spin, we can tell the spin, yeah, now, but we may have some handle if we look at the density fluctuation during inflation. And during inflation, if you have very large fluctuation, you will induce CMB and anisotropy as well as non-Gaussianity. And this is another thing it's good to look at to distinguish really the primordial black hole is really primordial or astrophysical. Thank you very much.
Where would these be distributed in the sky? Would they be associated with galaxies now, or are they just randomly formed by the?
You can imagine this. It's really like we have seen many large-scale structure movie. Yeah, each dot actually represents a primordial black hole. You can think about this. So it's now the halo, yeah. The dark matter, yeah, of course, this is really extreme. You can just imagine, if really primordial dark matter, you can measure dark halo. The dark halo actually is full of primordial black hole. The distribution is something like that. Then the distribution of that vector and that vector halo.
But they are source of numbers in the end, then shouldn't they just be the same distribution of the
Yeah, except yeah. Yes.
other questions? Okay, now let's
Okay, thank you.